Right, today's our last lecture on gases, and we're going to talk about gases in chemical reactions and Dalton's Law. All right, so far in our chemical reactions, we can easily go from a mole of one thing to mole of another using the coefficients. This was stoichiometry that we did a few chapters ago. And in that chapter, we also went from mass of one thing to mass of another thing going through moles. Okay, and then we also did calculations where we went from particles to moles, so we could do that direction as well. Today, what we're going to do is we're going to expand that a little bit more, and usually in gases, we aren't given a mass of gas. It's easiest to measure gases in terms of their volume. So now that we have the molar volume at standard temperature and pressure, and we also have the ideal gas law, we can easily get from volume of gas to moles of gas in a chemical reaction, and then go to another reactant if necessary. So we're going to do one example like that, and we'll do some more in class as well. Okay, so this first example is limestone, which is calcium carbonate, reacts with hydrochloric acid to produce aqueous calcium chloride, carbon dioxide gas, and water. Okay, and the balanced equation is there. So it says how many liters of CO2 are produced at 752 millimeters of mercury and 24 degrees Celsius from a 25.0 gram sample of limestone. Okay, so in this particular problem, we are looking for liters of CO2. So that will be our unknown. So the first thing you want to do is figure out what you're given and what you're trying to find. And the reactant that we're starting with is limestone, which is calcium carbonate. So we have 25 grams of that, and we want to figure out how much CO2 is produced. Okay, so we know from our previous slide, if we want to go from grams of one thing to moles of another thing, we have to go through moles first. So we're going to go from 25 grams of calcium carbonate to moles of calcium carbonate, and we're going to need the molar mass to do that. So that's 100.09 grams, and I got that from the periodic table, adding up all the elements. Okay, and then in our balanced equation, we can see that for every 1 mole of this we used, we make 1 mole of CO2. So our next parenthesis is just going to be a 1-to-1 ratio. Okay, and if we multiply all of that out, we get 0.2498 moles of CO2. All right, now from this point forward, or up till this point, all of this is review from things we've done in the past. Okay, so now the trickier part is combining this with what we just learned with the ideal gas law. So in this case, our pressure and temperature are not STP, so we're going to have to use the ideal gas law to get to the volume. So let's write out P, V, N, R, and T. And our pressure is going to be 752 millimeters of mercury, given on our problem. Our volume is what we're trying to find, how many liters of CO2. So that's going to be X. N, which is the number of moles, is what we just calculated. That's 0.2498 moles. R, in this case, is going to be 62.4 because we have millimeters of mercury for our pressure. And T is given as 24 degrees Celsius, which we're going to have to convert to Kelvin, and then it'll be 297 degrees Kelvin. Okay, so now what we want to do is just plug all that into our equation, and we'll have 752 times X is equal to 0.2498 times 62.4 times 297. Okay, so if we go ahead and solve for X, just using basic algebra, then we're going to get X equals 6.16 liters of CO2, and that's it. Okay, so the next thing we're going to do, the last law, is Dalton's Law, and this one is different than the other laws that we've done. It deals with partial pressure. So partial pressure is just the pressure that comes from one specific gas if you have more than one gas present in a container. So here, we only have our first gas, whatever it happens to be, in this container, the lighter colored one. And so that pressure is represented by P1. In the second container, we have a darker colored gas, which we're calling gas 2, and that has a given pressure. Okay, so you can tell here that the pressure in the second container is larger than the pressure in the first because there's more molecules present. Right? If we add those two things together, what you can see is that the pressure would go up even more, which you can see here on the gas gauge. And Dalton's Law tells us that if you have more than one gas in a container, then the partial pressures of each of the individual gases added together gives you the total pressure in the container. And this probably seems obvious, but this wasn't known for a little while. Scientists did experiments to figure out that this was true, that if you just combined two gases and you left the volume the same, that their pressures were just additive. Okay, so a very basic example for this. These problems are not going to be hard, it's just addition and subtraction. But in this example, we have heliox, which is a breathing mixture of oxygen and helium, and is prepared for a scuba diver who's going to descend 200 feet below the ocean surface. At that depth, the diver breathes a gas mixture that has a total pressure of 7 atmospheres. If the partial pressure of oxygen in the tank at that depth is 1.5 atmospheres, what is the partial pressure of the helium in the breathing mixture? So we're just going to use Dalton's equation. So we have two gases here, so our P total is going to equal the pressure of the helium plus the pressure of the O2. Okay, and we can see in our problem that the pressure of the the total pressure, is 7.00 atmospheres. Pressure of helium is what we're looking for, and the pressure of the oxygen is given as 1.5 atmospheres. So we can plug that in there. Okay, so if we then go ahead and solve for the pressure of helium, we get 5.5 atmospheres. All right, so very simple. And this wraps up our discussion of the gas laws. We're going to do a little more practice in class and work with these a little bit more in the lab and do some practice problems.